Welcome! In this session, we'll explore an exciting problem called Find Leaves of Binary Tree. This problem involves breaking down a binary tree into its leaf nodes layer by layer. We'll walk through the approaches, analyze their complexity, and provide key insights to help you master this challenge. Let's dive in. In this problem, we're tasked with finding the leaves of a binary tree in a specific iterative manner. The process works like this. First, we collect all the leaf nodes of the tree. Then, we remove those leaf nodes from the tree, and repeat the process, collecting the new leaf nodes during each iteration. We continue this process until the tree is completely empty. The goal is to return a list of lists, where each inner list represents the nodes collected during one iteration. To clarify, the input to the problem is the root of a binary tree. Each node in the tree is structured with three properties: a val, which is the integer value of the node, and pointers to its left and right children, which could be either another node or none if a child doesn't exist. The output is a list of these collected values, grouped by the iteration in which they were removed from the tree. To understand this better, let's look at an example. Suppose the input is a binary tree with the structure shown here, where the root node has the value 1, and it has two children, 2 on the left and 3 on the right. Node 2 further has two children, 4 and 5, while node 3 has no children. During the first iteration, the leaf nodes are 4, 5, and 3. After removing these nodes, the tree is reduced to just the root node 1 with its left child 2. In the next iteration, the new leaf node is 2, which is then removed, leaving us with only the root node 1. Finally, in the last iteration, the root node 1 is removed, leaving an empty tree. The output for this example is a list of lists: 4, 5, 3, 2, 1. Continuing with that explanation, we can break down the steps of the process further. After removing the initial set of leaf nodes 4, 5, and 3, the tree structure simplifies to just node 1 with its left child 2. In the second step, the new leaf node is 2. Removing it reduces the tree to just the root node 1. Finally, in the third step, the root node 1 is removed, leaving the tree empty. This iterative process results in the output 4, 5, 3, 2, 1. Now, let's take a look at a simpler example where the tree consists of just a single node. Here, the input is a binary tree with only one node, the root node with the value 1. In this case, the process is straightforward. During the first step, the only node in the tree 1 is also the only leaf node. Once it's removed, the tree becomes empty. Since there was only one iteration, the result is simply 1. This demonstrates how the method works even with the simplest possible tree structures. Next, let's consider a more complex example where the tree is slightly unbalanced. In this case, the root node is 1, and it has two children, 2 on the left and 3 on the right. Node 3 further has two children, 4 and 5, while node 2 has no children. In the first step, the leaf nodes are 2, 4, and 5. Removing these nodes leaves a tree with only the root node 1 and its right child 3. In the second step, the new leaf node is 3, and removing it leaves just the root node 1. Finally, in the third step, the root node 1 is removed, leaving the tree empty. The output for this example is 2, 4, 5, 3, 1. We are also given some constraints and edge cases to consider. For instance, the number of nodes in the tree will always be between 1 and 100, and each node's value will be within the range of -100 to 100. Additionally, edge cases include single-node trees, trees where all nodes are leaves in the first step, highly unbalanced trees, and larger trees with the maximum number of nodes. These constraints ensure that our solution needs to handle a variety of scenarios efficiently. To begin solving this problem, let's consider a straightforward brute force approach. In this method, we repeatedly identify and collect all the leaf nodes of the tree. A helper function can recursively traverse the tree to find nodes without any children, which are the leaves, and return them. Once these leaf nodes are identified, we remove them by setting their parent pointers to none, and then repeat the entire process on the remaining tree. This process continues until the tree is completely empty. However, this approach has significant drawbacks. The time complexity can grow to O(n squared) in the worst-case scenario, such as in a skewed tree, where each level involves traversing all the remaining nodes. Additionally, it requires O(h) space for the recursion stack, where h is the height of the tree. While simple to understand, this method is inefficient for larger trees due to repeated traversals and the associated computational overhead. Now, let's explore a more efficient approach that leverages post-order traversal and depth-based grouping. The key idea here is to calculate the depth of each node as we traverse the tree. Using post-order traversal, where we process the left subtree, then the right subtree, and finally the root, we can determine each node's depth based on the maximum depth of its left and right subtrees, plus 1. This depth uniquely identifies the round in which a node will be removed. As we traverse, we group nodes into lists based on their depth. This allows us to organize all nodes into their appropriate levels in a single traversal. By the end, we have a result list where each group corresponds to a round of leaf removal. This approach eliminates the inefficiencies of repeated tree modifications, making it significantly faster and more streamlined. The brilliance of this optimized approach lies in a few key observations. First, a node's depth directly corresponds to the round in which it will be removed from the tree. This insight allows us to avoid modifying the tree entirely, instead focusing on computing and organizing nodes by their depth in one pass. The time complexity is O(n), since each node is processed only once during the traversal. Space complexity remains O(h), where h is the height of the tree, due to the recursion stack. This method is not only optimal in terms of performance but also elegant in its simplicity. However, it does require a solid understanding of post-order traversal, which might pose a slight learning curve. Overall, it successfully balances efficiency and clarity. Given the trade-offs between the brute force method and the optimized approach, the latter is clearly the better choice. The optimized approach is efficient, solving the problem in a single traversal and minimizing redundant work. It also avoids the need to modify the tree structure, which is safer and maintains the integrity of the tree. By grouping nodes based on their depth, we achieve a clean and intuitive solution that is both conceptually and computationally superior. In conclusion, the post-order depth-based grouping approach strikes the right balance between simplicity, performance, and memory usage, making it the ideal strategy for solving this problem effectively. To solve this problem, we need to repeatedly remove all the leaf nodes from a binary tree until the tree becomes empty, while collecting the leaves removed at each step. A leaf node is one that has no children, meaning both its left and right pointers are null. At each iteration, we identify all the current leaf nodes, collect them, and then remove them by setting their parent pointers to null. This process is repeated until the tree is fully removed, and we return the collection of leaves grouped by the order in which they were removed. A recursive helper function can be used to identify and remove leaves. This function traverses the tree, checks if a node has no children, and if so, marks it as a leaf and adds its value to the current collection. Once the children of a node are processed, the leaves are removed by setting the corresponding child pointers to null. The main function uses a while loop to repeatedly call the recursive helper function until the entire tree is empty. During each iteration, we maintain a list called result to store the collected leaves. The leaves found at the current level are appended to this result list. The recursive traversal ensures that we process the deepest leaf nodes first, working our way upward as the tree is reduced in size. By modifying the tree in place, setting parent pointers to null after removing leaves, we avoid the need to create new tree structures, making the algorithm space efficient. Each node is processed exactly once throughout all iterations, leading to a time complexity of O(n), where n is the number of nodes in the tree. The input to this problem is a binary tree, where each node contains a value and pointers to its left and right children. To store the leaves collected at each iteration, we use a list called result. The recursive function for identifying and removing leaves works as follows: if the current node is null, it simply returns null. When a node has no children, its value is added to the current level's leaf collection, and null is returned to indicate that the node has been removed. For non-leaf nodes, the function is called recursively on the left and right children, and their pointers are updated based on the returned values. After processing, the current node is returned, unless it is identified as a leaf in that iteration. The main function begins by initializing an empty list called result to store the leaves collected at each level of the process. While the root of the tree is not null, indicating that the tree is not yet empty, we initialize another list, current_leaves, to collect the leaves for this iteration. The recursive helper function is then called on the root, with current_leaves passed as a parameter to collect the leaves. Once the leaves are collected, they are appended to the result list, and the process continues until the tree is fully removed. Finally, the result list, which contains all the collected leaves grouped by iteration, is returned. This approach handles various edge cases, such as empty trees, trees with a single node, and skewed trees resembling linked lists. The space usage of this algorithm depends on the height of the tree because of the recursive call stack. For a balanced tree, the height is proportional to log n, so the space complexity is O log n. However, for a skewed tree, where all nodes are either to the left or right, the height is equal to the number of nodes, resulting in a space complexity of O n. In terms of time complexity, each node is visited exactly once during the entire process, leading to an overall time complexity of O n. Let's take an example to better understand the algorithm. Consider a binary tree where the root node has a value of 1, with two children, 2 and 3. Node 2 has children 4 and 5, while node 3 has a right child, 6. In the first iteration, we collect the leaf nodes, which are nodes with no children. These are 4, 5, and 6. After removing these leaves, the remaining tree consists of the root node 1 and its two children, 2 and 3. In the second iteration, the new leaf nodes are 2 and 3, as they now have no children. Removing these leaves leaves us with only the root node, 1. In the third and final iteration, the last remaining node, 1, is removed, leaving the tree empty. Each iteration collects the current leaves, and the tree is reduced step by step until it is fully removed. The final output is a list of lists representing the leaves collected at each iteration. For the given example, the output is 4, 5, 6, 2, 3, 1. This means that in the first iteration, we collected the leaves 4, 5, and 6. In the second iteration, we collected 2 and 3, and in the final iteration, we collected the root node, 1. This illustrates how the algorithm progressively removes all nodes from the tree, grouping the leaves by their levels of removal. The provided Python solution addresses LeetCode problem number 366, find leaves of binary tree. The task involves removing all leaf nodes from a binary tree iteratively and returning the leaves collected at each stage. Let us break this solution down. 1. Outer function definition. The findLeaves method is defined as part of the solution class. It takes the root of the binary tree as input and initializes an empty list result, which will store the leaves grouped by their removal stage. 2. Helper function, DFS. Inside the method, a nested helper function DFS is defined to perform a depth-first traversal of the tree. This function calculates the height of each node, distance from the farthest leaf. 3. Base case. The base case checks for a null node. If the node is null, its height is considered -1, indicating it does not contribute to the tree structure. For recursive calls, the DFS function recursively calculates the height of the left and right children of the current node. 5. Node height calculation. The height of the current node is determined as max, left_height, right_height, plus 1. This ensures that the node's height reflects its depth in the tree during leaves removal. 6. Result list management. If the current height equals the length of the result list, a new list is appended to accommodate nodes at this height. This ensures that each height level corresponds to a unique sublist in result. 7. Node value addition. The current node's value is added to the sublist corresponding to its height. This groups nodes by their removal stage. 8. Return height. The function returns the computed height for the current node to aid in the parent node's height calculation. 9. Final return. After the DFS function completes, the result list contains all leaves grouped by their removal stages, and it is returned as the output. This solution is efficient, as each node is visited once, resulting in a time complexity of O, n, where n is the number of nodes in the tree. The space complexity is O, h, where h is the height of the tree, due to the recursive call stack. This implementation is both clean and optimal for the given problem. Here, we begin our Java implementation for finding the leaves of a binary tree. The main method, findLeaves, initializes a list of lists called result to store the nodes grouped by their height levels. It then calls a helper function, DFS, which performs a depth-first traversal to calculate the height of each node. If the current node is null, the function returns -1, indicating that we've reached the end of a branch. Next, the function recursively calculates the heights of the left and right children. Using these values, the height of the current node is determined as 1 plus the maximum of the left and right heights. To ensure that the result list can accommodate this height, we check if the height matches the current size of the list. If it does, we add a new empty list to represent this height level. Once we've ensured the result list can store the current height level, we add the value of the current node to the corresponding list. Finally, the function returns the calculated height of the current node, which allows the parent nodes to determine their own heights. The tree node class is defined at the bottom of the slide, representing the structure of each node in the binary tree. It includes fields for the node's value and pointers to its left and right children. This implementation effectively groups the nodes by their heights, with the leaves being at height 0, their parents at height 1, and so on, enabling us to collect the leaves layer by layer. To begin solving the problem, we start with the given binary tree. The root node has a value of 1, with left and right children having values 2 and 3, respectively. We invoke the findLeaves function with the root node, initializing an empty list called result to store the nodes grouped by their heights. Next, we initiate a depth-first search, DFS, starting with the root node. When processing node 1, since it is not null, we proceed to explore its left subtree by calling DFS2. Similarly, at node 2, which is also not null, we continue deeper into its left subtree by calling DFS none, as node 2 does not have a left child. When the DFS reaches a null node, such as the left child of node 2, it immediately returns a height of -1, indicating no further depth from this path. Backtracking to node 2, we now examine its right child, which is also null, resulting in another height of -1. With heights from both children calculated, we compute the height of node 2 as the maximum of these two heights plus 1, yielding a height of 0. At this point, we ensure the result list has a space for height 0 by appending an empty list if necessary. We then add node 2's value to result 0, making result equal to 2. The height of node 2 is returned to its parent, node 1. Next, we explore the right child of node 1 by calling DFS3. At node 3, we observe that it is not null, so we proceed to check its left and right children, both of which are null. For each null child, the DFS returns a height of -1. The height of node 3 is then calculated as the maximum of these two heights plus 1, resulting in a height of 0. We add node 3 to result 0, updating result to 2, 3. The height of node 3 is returned to node 1. Now, with heights obtained from both children of node 1, we compute its height as the maximum of 0 and 0, plus 1, which gives a height of 1. We ensure result has space for height 1 by appending an empty list if needed, and then add node 1 to result 1. The final result for this tree is 2, 3, 1, which we return as the output. For the second example, the binary tree is unbalanced, with nodes 1, 2, and 3 forming a left-skewed structure. We start by calling findLeaves with node 1 and initializing result as an empty list. Beginning with the root node, we invoke DFS1, which leads to a recursive call on its left child, node 2. At node 2, we further recurse into its left child, node 3. At node 3, we attempt to explore both its left and right children, both of which are null. Each null child results in a height of -1 being returned. The height of node 3 is then calculated as the maximum of these two heights plus 1, giving a height of 0. We ensure the result list has space for height 0, appending an empty list if necessary, and add node 3 to result 0. This makes result equal to 3. The height of node 3 is returned to its parent, node 2. Back at node 2, we now inspect its right child, which is null, resulting in a height of -1. Using the height of 0 from node 3 and -1 from the null right child, we compute the height of node 2 as the maximum of these values plus 1, resulting in a height of 1. We ensure result has space for height 1, appending an empty list if necessary, and add node 2 to result 1. The result list is now 3, 2. The height of node 2 is returned to its parent, node 1. Next, at node 1, we examine its right child, which is null, resulting in a height of -1. Using the height of 1 from node 2 and -1 from the null right child, we calculate the height of node 1 as the maximum of these values plus 1, giving a height of 2. We ensure result has space for height 2, appending an empty list if needed, and add node 1 to result 2. The final result for this tree is 3, 2, 1, which we return. In the third example, we are given a full binary tree where node 1 is the root, nodes 2 and 3 are its children, and nodes 4 and 5 are the children of node 2. Starting with find leaves invoked on node 1, we initialize result as an empty list. The DFS begins at node 1, moving to its left child, node 2. At node 2, we delve into its left child, node 4. Node 4 has no children, so recursive calls to DFS, none, for both its left and right children return -1. The height of node 4 is computed as 0, and we add its value to result, 0, making result equal to 4. The height of node 4 is returned to its parent, node 2. Next, node 2's right child, node 5, is processed in a similar manner. Recursive calls to DFS, none, for both children of node 5 return -1. The height of node 5 is calculated as 0, and we add its value to result, 0, updating result to 4, 5. The height of node 5 is returned to node 2. Back at node 2, with heights of 0 from both children, we compute its height as 1. We ensure result has space for height 1, appending an empty list if necessary, and add node 2 to result, 1. The result list is now 4, 5, 2. The height of node 2 is returned to node 1. We then process node 1's right child, node 3. Since node 3 has no children, recursive calls to DFS, none, for both of its children result in heights of -1. The height of node 3 is computed as 0, and we add its value to result, 0, updating result to 4, 5, 3, 2. The height of node 3 is returned to node 1. Finally, at node 1, with heights of 1 from node 2 and 0 from node 3, we calculate its height as 2. We ensure result has space for height 2, appending an empty list if needed, and add node 1 to result, 2. The final result for this tree is 4, 5, 3, 2, 1, which is returned as the output. The time complexity of this solution is O, n, where n represents the number of nodes in the binary tree. This is because the algorithm performs a depth-first search, or DFS, to traverse the tree. During the traversal, each node is visited exactly once. For each node, the algorithm performs two key operations. It computes the height of the left and right subtrees, and it adds the node's value to the appropriate position in the result list. Both of these operations are constant time, or O1. Since there are n nodes in the tree, the total time complexity is O1 multiplied by n, which simplifies to O(n). This linear relationship ensures the algorithm is efficient, as the time spent processing the tree grows proportionally with the number of nodes. Now, let's discuss the space complexity of the solution, which is O(h), for the recursion stack and O(n) for the result list, where h is the height of the binary tree. First, the recursion stack space is determined by the depth of the DFS traversal. In the best case, where the tree is perfectly balanced, the height h is log n. In the worst case, such as a completely skewed tree, the height h equals n. Thus, the recursion stack requires O(h) space. Next, the result list stores all the nodes of the tree grouped by their heights. Since every node is added exactly once to this list, it requires O(n) space. Combining these two components, the total space complexity becomes O(n) plus h. To summarize the total space complexity, we combine the recursion stack space and the result list space, leading to O(n) plus h. In the best case, where the tree is perfectly balanced, this simplifies to O(n) plus log en. In the worst case of a completely skewed tree, it becomes O(n) plus n, which is O(n). Comparing this to a naive approach, where all leaf nodes are repeatedly removed in separate passes, the given solution is significantly more efficient. A naive method would involve n passes, with each pass traversing the tree, leading to a time complexity of O(n) squared. Instead, our approach determines the height of all nodes in a single DFS traversal, reducing the time complexity to O(n). This optimization not only avoids redundant traversals but also efficiently organizes nodes by height in the result list, making the algorithm both time and space optimal. Let's analyze the best, average, and worst cases for our solution. In the best case, where the tree is perfectly balanced, the height of the tree is log n. The time complexity remains O(n), as we still visit all nodes exactly once, and the space complexity becomes O(n) plus log n, due to the recursion stack and result list. For the average case, where the tree is partially balanced, the time complexity remains O, n, while the space complexity is O, n plus h, where h depends on the specific structure of the tree. In the worst case, if the tree is completely skewed with all nodes in a single line, the height becomes n. Here, the time complexity is still O, n, but the space complexity becomes O, n plus n, which simplifies to O, n. Finally, let's provide a mathematical proof for both time and space complexity. In terms of time complexity, each node in the tree is visited exactly once during the DFS traversal. For each node, the operations of calculating its height and appending its value to the result list are constant time operations. Therefore, the total number of operations is directly proportional to the number of nodes, giving us O, n. For the space complexity, the recursion stack depth is equal to the height of the tree, which is h, and the result list holds values for all n nodes. When we combine these, the total space complexity becomes O, h, plus O, n, which simplifies to O, n plus h. This concludes our analysis, showing that the algorithm is both time and space efficient. When solving tree-based problems, it's important to first understand the constraints given in the problem. For example, if the tree is specified as a balanced binary tree or follows binary search tree properties, these constraints can significantly simplify the solution. Ignoring them might lead you to write overly complex or incorrect code. Another common mistake is recomputing subproblems in recursive solutions. For instance, when calculating the height of a subtree, failing to store intermediate results could lead to redundant calculations and increase runtime unnecessarily. A simple optimization, like memoization, can make a big difference. Additionally, edge cases should never be overlooked. Situations like an empty tree, a single-node tree, or trees with only one child often lead to runtime errors if not handled properly. Finally, traversal order is critical. Problems that require processing child nodes before their parent typically rely on post-order traversal, while confusing this with a different order, like pre-order, can result in incorrect outputs. Now, let's look at some tips to refine your approach. Overcomplicating base cases in recursive solutions can make debugging a nightmare. Instead of handling multiple null checks individually, try consolidating them into a simpler condition. Recognizing patterns in tree problems can also help you solve them more effectively. For instance, many tree problems rely on common strategies like depth-first or breadth-first search, divide and conquer, or even dynamic programming. Choosing the right traversal order is equally important. For example, post-order is great for bottom-up calculations, like determining the height of a subtree, while pre-order works well for top-down calculations, such as propagating path sums. When it comes to recursion versus iteration, recursive solutions tend to be more intuitive for trees, but interviewers may prefer iterative implementations because they avoid stack overflow issues. Finally, be prepared to discuss space optimizations, comparing the implicit recursion stack space of O, H, to the explicit stack used in iterative solutions. Understanding these trade-offs demonstrates a thorough grasp of the problem. To deepen your understanding, it's helpful to explore related problems that emphasize different aspects of tree algorithms. For example, LeetCode 543, the diameter of binary tree, uses post-order traversal to calculate subtree heights, which is a similar concept to finding leaves in a bottom-up manner. LeetCode 124, binary tree maximum path sum, combines divide and conquer with dynamic programming, offering a great example of how these techniques can be used together. If you're looking for a simpler problem to practice traversal, LeetCode 226, invert binary tree, is a great choice, as it can be solved using either a recursive or iterative approach. Lastly, LeetCode 230, kth smallest element in a BST, demonstrates how in-order traversal leverages the properties of binary search trees to efficiently locate specific elements. Solving these problems will strengthen your ability to recognize and apply the right strategies for tree-based challenges. Finally, let's consider some alternative approaches and their trade-offs. A naive recursive approach can be very straightforward to implement, but it often results in inefficiencies due to redundant calculations. This method is best suited for problems with small input sizes where performance isn't a major concern. On the other hand, dynamic programming with memoization is a more efficient option, as it avoids recomputation by storing intermediate results. The trade-off here is the extra space required for memoization, making it ideal for problems involving overlapping subproblems, like finding maximum path sums. An iterative approach using a stack or queue can also be a good alternative. While it avoids the risk of exceeding recursion depth, it tends to be more complex to write and debug. Iterative solutions are particularly useful in environments with low recursion limits or when you need explicit control over the traversal order. Understanding which approach works best for a given problem will help you write both efficient and elegant solutions. Great job! To wrap up, we reviewed the problem Find Leaves of Binary Tree, analyzed its complexities, and highlighted key takeaways like recursive tree traversal and understanding problem decomposition. Thanks for joining, stay curious and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!